We're going to move to the next talk is by Viktor Khalack from Université de Moncton. I said correctly. And we're going to hear some about the chemical peculiar style with ESPaDONS.
Hi everybody, my name is Viktor Khalack, Université de Moncton, New Brunswick, and eastern part of Canada, still Canada. So I would like to present you some results on spectropolarimetric observation of chemically peculiar stars performed during recent years with ESPaDONS. So if we are talking about chemically peculiar stars, naturally they have different chemical abundance in the stellar atmosphere with respect to the solar one, which is well published in many articles of Aslum, Grevesval, etc. And usually abundances are measured with respect of chemical elements are measured with respect to the abundance number of hydrogen atoms. So it's well known that 10-15% of main sequence stars are chemically peculiar. Some of them are magnetic stars, so they show signatures of magnetic field according to spectropolarimetric, photopolarimetric measurements, while another do not show any signatures of magnetic field, though some people claim that Mercury-manganese stars still show magnetic field signature. And here we have as well delta Scuti and lambda Boötis stars still also considered as chemically peculiar. Again, considering that some CP stars possess signatures of show signatures of magnetic field, so we can measure them through the photo or spectropolarimetry. And historically, first star for which magnetic field was measured is 78 Virginis. It's Babcock Jr., 1947, when his father measured solar magnetic field, he used a Zeeman analyzer to measure magnetic field in stars. So I will jump directly to spectropolarimetry when Matisse has proposed to use a moment technique to measure mean effective magnetic field and mean surface magnetic field using Stokes I and V spectra. And and here you can see on the image Stokes I and quite significant signal is Stokes V signal, Stokes V profile for this newly discovered ρ star. So after Jean-François Donati proposed least square deconvolution method to measure mean longitudinal magnetic field, we derived magnetic field for this particular target, and we see that Bz is decreasing slowly this year because we found for this particular target 50 years rotational period that due to the observations done 30 years ago. So, least square deconvolution methods proposed by Jean-François Donati that take into account the signal stored in thousands of line profiles observed in spectra to calculate the final LSD profile from which we can derive mean longitudinal magnetic field with high precision. This method was improved by Oleg Kochikov, that takes into account more line intensity of line profiles, and recently Dr. Colin Folsom and his team have implemented this method in SpectPool flow. So thank you, Colin and Christy Erba and the whole team that worked on that. And now everybody can use this method to measure mean longitudinal magnetic field. So here you can see on the top it's Stokes V profile, where signal is quite visible. Second from the top, it's a noise. So here we're checking if there is some leaking from instrumental polarization, or we do have some leaking from Stokes Q and U, and below we have Stokes I profile for this target. We measured magnetic field with precision of 20 Gauss. So following these methods, we selected some interesting targets like APBP stars from test photometry. Those targets show rotational modulation, pulsation like ρ, and we started the observation with ESPaDONS at CFHT starting from 2020s up to date. So here is a cumulative table, and you can see we acquired like few spectra each semester, and you can ask why to do this. And apparently, each of these stars show rotational modulation, so we need to cover all the rotational phases properly to have possibility to do Zeeman Doppler imaging and reconstruct the structure, configuration of magnetic field, and horizontal abundance stratification. So here you have a few examples. New recently discovered Rho AP star HG210684, for which we obtained more than 10 spectra, and you see beautiful variation and significant variation in Stokes V profile LSD. If you look individually for a particular chemical element, you will see nothing, no signal. But you see, like here, 7,000 lines. We can see some signal is present. Period rotation derived from photometry, and two spectra taken at different seasons show and phase it at the same rotational phase show exactly the same line profile. So period is good, but when we derive it mean Bazet, we see that field is very weak, around 100 Gauss, and definitely not dipole. Instead, we have second star is a well-known magnetic APBP star, for which as well we have nice measurements of variability of Stokes V profile, and our magnetic field measurements are in good accordance with BTI 6-meter telescope measurements. So it's again good targets for ZDI, but we still have some gaps in rotational phases that should be covered, so we need more observations. Sorry. We also aim to observe Mercury manganese star. They are members of binaries and show tidal and G-mode pulsations. So to do the proper abundance analysis and try to measure magnetic fields if they are present, because some people claim they are there. So we asked it to observe those star targets with spectropolarimetry. We started with neon narval, and for wiki targets we continue with ESPaDOnS. So here is a cumulative table again, and just to show you some targets like HD 19229, for which we have more than 10 spectra, and in this case, Stokes VLSD is the same as Stokes N, so noise, no magnetic field, detected as a precision 3 Gauss. During 5 semester observation were done, but another star HD, a well-known binary 89822, again, magnetic field is 0. But some data for this obtained with ESPaDOnS from this star were used by master student for his master thesis, where he studied tidal pulsations. Again, other interesting targets are delta Scuti stars, some of which show magnetic field. Therefore, we selected targets from test photometry that show P-mode pulsation at high overtone frequencies, more than 40 cycles per day. We proposed some targets for observation with ESPaDOnS, and recently Thomson-Parson said, okay, guys, please look for rotational modulation. That might be signature of magnetic field present. So here are the targets already observed. We have analyzed them, and only one known magnetic delta Scuti star show signature of magnetic field. As an example, HD 71297, you see Stokes V is exactly like Stokes N, 0 magnetic field detected with precision 1.5 Gauss, or even 2 Gauss, still 0 field. Others, 14 delta Scuti stars show similar results, but for known magnetic star, we have derived 113 plus minus 11 Gauss magnetic field, and this result was used by my master student, Margarita Slusarenko, for her thesis. So, what's next? Considering that Stokes I and V spectra derived from ESPaDOnS pure result in accurate measurement of mean longitudinal magnetic field, we plan to observe Rho AP stars, and new type of stars recently appears, super slowly rotating AP stars with Spiru. So we plan to observe them next semester and continue to observe them. And considering that I am a member of Canadian aerial team, it's a space mission of European Space Agency that will be something, will observe stars with exoplanets. So aim is to use some of these targets to observe them with SPIRO, to check if they have magnetic field signatures or not, because it's important for the further analysis of spectrum that can be from exoplanets. This, as well, the next idea is to take in consideration available ESPaDOnS and SPIRO spectra to develop the best strategy for observation of chemically peculiar stars, simultaneously with both those instruments using the Lac-à-l'Eau-Claire. So, and finally, I would like to acknowledge and thanks to my students that continuously applied for observation of CP stars with ESPaDOnS. I would like to thank to CFHT team for their good, excellent work to helping me to obtain good spectra with high signal-to-noise ratio. And I would like to thank to this team that they carry out the observation of the summit of Mauna Kea with respect to the culture and tradition of Hawaiian people. Thank you for all the organizations that supported this research, and thank you for your attention.
Question for Viktor.
Thank you, Viktor, for this presentation. Why do we think that delta Scuti stars are chemically peculiar?
Again, can you repeat?
Why do we think that delta Scuti stars are chemically peculiar?
Delta Scuti. So when we said, like by definition, if chemical abundance is different than from the solar one. Some early observation of 1990s, 1980s showed that some chemical elements show different abundance than solar abundance. So in general, we can consider them as, like, according to this approach, as chemically peculiar.
And do you confirm that?
I haven't done abundance analysis, so sorry I cannot confirm that. But I trust people who published articles.
Any other question? If not, I think let's thank Viktor again.
Thank you.